Today's lesson is about absolute value graphs. So if you think back to the definition of absolute value, the absolute value of x is equal to x if x is greater than or equal to 0, or it's equal to negative x if x is less than 0. So what we've got here are the graphs of y is equal to x and y is equal to negative x. So when we're looking at the absolute value of x, our definition tells us that it is equal to x, so it's equal to this first graph when x is positive, so when it's greater than or equal to 0. So that means these ones just here. But if x is less than 0, it doesn't use this graph. It uses negative x. So when x is less than 0, it uses these ones here. So what that means when we combine them is that we get a graph that looks like this. So this is the graph of y equals the absolute value of x. So absolute value graphs all have this V shape. It's just about how far they move. So you just have to figure out where is their turning point, how steep to make it, and then off you go. So if we look at these ones here, so we've started off with the one we just did, y equals the absolute value of x, and I want to know what's going to happen if you get y is equal to the absolute value of x and you subtract 1. Now the trap here is that a lot of students think, oh, there's an absolute value sign, so it can never be negative, but only the x is in the absolute value sign, so the x can't give you a negative value, but then when you subtract 1 from it, you can get a negative value. So look for some of the important points. For instance, when x is equal to 0, what happens if we substitute that in? When x is equal to 0 and then we subtract 1, we get minus 1. Where's it going to cross the x-axis? Well, for the x-axis, y is equal to 0, the x-intercept, so when y is equal to 0, and that's going to happen when x is equal to 1 and x is equal to negative 1. Now, once you've got the turning point and a couple of other intercepts, it's pretty easy to fill in the rest of the graph. So that's our graph of y equals the absolute value of x minus 1. So what happens if I move the minus 1 inside the absolute value brackets? Well, think about the lesson that we did where we were looking at all those graphs. When we put the constant that we're adding or subtracting inside, the graphs moves left to right, not up and down. When we subtracted 1 after we did the absolute value sign, the whole graph dropped 1 unit. But if we're putting the minus 1 inside and then working out the absolute value, then we're going to be moving to the right. Now, if you can't reason your way through it, then just substitute in some numbers and some important numbers that are going to give you the intercepts. So when x is equal to 0, we get y is equal to the absolute value of negative 1, which is 1. When x is equal to 1, we get the absolute value of 0, so that's 0. And when x is equal to 2, 2 minus 1 is 1, absolute value of 1 is 1. So there you've got a few points that you can then join up to work out your absolute value graph. So drawing the absolute value graphs can help us to understand why when we had those absolute value equations, sometimes we got 2 valid solutions, sometimes we had 1 valid solution, and sometimes we had none. So even though we solved it and we found values for x, when we substituted them back into the absolute value equation, they didn't work. This is why. So if you've been given the equation 2x minus 4 is equal to the absolute value of 4x plus 1, what happens when I graph those two functions separately? Well, 2x minus 4 gives me this straight line you can see here. It has a y-intercept of negative 4, x-intercept of 2, positive gradient, and so it looks like that. And the absolute value of 4x plus 1 looks like this graph you can see here. So that's going through negative a quarter, cuts the y-axis at 1. The two graphs don't meet. they never intersect. So even if you can solve this equation, like go 2x minus 4 equals 4x plus 1 and find a value for x, when you substitute it back in with the absolute value signs, it doesn't work. This is why. Because the two don't meet. There is no single point on this graph that satisfies both of those equations. So this has no valid solutions. Now looking at a second example, this is the absolute value of 2x plus 1 is equal to 6x minus 3. So you can see the straight line, 6x minus 3, and the absolute value of 2x plus 1. And in this case, there is one valid solution, which in this instance is 1, which makes sense if you substitute that back up into the absolute value equation. 2 times 1 plus 1 is 3, so the absolute value of 3 is 3. 6 times 1 minus 3 is 3. Both sides are equal, so that is a valid solution. There is one point where they intersect, so this has one valid solution. And then other cases were like this. So if we do x plus 3, that's our straight line, and then we've got the absolute value of 2x, so that's that V-shaped graph. And in this case, we have two valid solutions. So x is equal to 3 and x is equal to -1. And again, you can check that by putting that up into your equation, but both of them work this time. And that's why you always had to check, because you can't tell simply by looking at your numbers which of them were valid and which ones weren't. Absolute value inequations can also be solved graphically. So what you do is, again, you split it into the two and you graph 2x minus 1, and then you graph y is equal to 5. So you can see the two there. And then we're looking for where the graph of the absolute value of 2x minus 1 is less than 5. Well, that is this part here. So what values solve that? Well, x lies between -2 and 3. So if you are finding graphing the absolute values easy, this can be another method for solving absolute value inequations if you are finding the other methods a bit tricky. So here's another one, the absolute value of x plus 1. So you can see that graph there, and we want to know when is that greater than or equal to 3. So we've got the line y is equal to 3. It's greater than or equal to at these values here. So what that means is that x has to be greater than or equal to 2, or x has to be less than or equal to -4. So again, if you find drawing absolute value graphs easy, then this is another method that you can use to solve them. If you prefer the algebraic method, you're welcome to do that. It's whatever works for you guys, okay? So for exercise 5.6, I want you to do some of each question. Okay, don't skip question 2 or question 3. Do a bit from each. You'll see there's quite a lot to choose from. Make sure you cover a variety. And if you're finding drawing these graphs difficult, do a lot. Good luck, and I'll see you in class.